Hello class, this is a continuation on dilations. So let's get straight into our second example. In this example, we're going to dilate this function by a factor of 1.5 this time. Before we even begin, if ever you notice that we have a function that can be factorized, it'll make it easier later on to do so. So in this case, we can factor it by two numbers. I can see it's going to be positive 3 and negative 5. So our function that we're working with is this one. So now to dilate this vertically by a factor of 1.5, you can do this with a decimal. But I'd like for you to think of this as 3 over 2. And you'll see why thinking of it this way will improve your algebraic techniques. But also for later on, you'll see how it'll work out. So to dilate something vertically, we are replacing y with y over the factor. In this case, it's going to be y over 3 over 2 equals f of x. Since we have a fraction in the denominator, you can think of this as y divide 3 over 2. Which is y times 2 over 3. So this becomes 2y over 3 equals f of x. So now to make y the subject, this would become y equals 3 over 2 times f of x, or you can think of this as 3 times f of x divided by 2. So 3f of x all over 2. This is the way we can think of this. So for this, writing this out using this one, we can simply write this as y equals 3 times x plus 3, x minus 5, all over 2. Or we could write it as 3 over 2 times the two groups. You could expand this, but it's already factored for us, so we may as well just leave it like so. So now, that is how we have done it algebraically. The graphical representation of this now, let's do this in blue. Since this is a vertical a vertical dilation, we look at the distances of the function, and we look at its current distance, and we're going to multiply that by 1.5 or times it by 3 over 2. So doing so, 9 times 3 over 2, this becomes 13.5. So this point becomes 13.5. 11, 12, 13.5, and since it's a parabola, it would be identical for this point here as well. So these 2 points will now be moved here. Since these points, the distance from the x-axis or the y value is currently 0, if we were to multiply that by 1.5, this point will not move. So here we are. And now for negative 16, its distance is currently negative 16. So multiplying that by 1.5, we will get negative 24, which would be all the way down here. Looking at those points, we can see the vertically dilated function like so. And we can extend this. In actual fact, we missed a little point here. That point would be 15, and just to clarify what that new y-intercept would be, negative 15 times 1.5 should be negative 22.5. 0.5. Now, it looks like the scale is not quite correct in this, but I hope you still get the idea that that point there should be negative 22.5 as our y-intercept. So now let's move on to the horizontal dilation. Likewise for this, we're going to substitute. So it's going to be y equals f of x over 3 over 2. And by the same logic as this one, I'm just going to express it as y equals f of 2x over 3. In case you're wondering how we got from here, just recall how we did it for the y values here. So now substituting x for 2x over 3 into both of these, we will get y equals x plus 3, x minus 5. So now I'm getting ready to substitute it to these points. And now substituting the transformation, 2x over 3, 2x over 3. And now combining both of these into one fraction, this will become all over 3. 2x hasn't changed. Since this is over 1, its denominator has been multiplied by 3. So this will become 2x plus 3. Oh, sorry, plus 9. My apologies. And this one as well, this will become all over 3. Now remember, this is currently over 1, so this has been multiplied by 3. So the new numerator will become negative 15. From this group, we're going to factor out 1/3. And from this group, we're also going to factor out 1/3. Those two coefficients of the groups, those multiply to give us 1 over 9 times 2x plus 9, 2x minus 15. Or we could write this as all of this all over 9. So now with this new transformed function, we can look at this. We're going to look at these points and graph them with the graph. So this time, because we are looking at the horizontal dilation, we look at the x values of the original graph. So let's take a look at this one. 6 times 1.5, that point will become 9. So this will be moved out to become 9. Whoops. Likewise for this one, 5 times 1.5, 7.5 will be moved to here. And that would actually correspond to this intercept, because if you did 2x minus 15 equals 0 and solve for x, you get x equals 7.5. Okay, we have 2 points now. This point still has an x distance, 1 times 1.5. Well, that will become 1.5. So that point is moved very little, just to the right. This point here does not move because its x distance isn't moving left or right, so that is still the same point. 3 is going to be moved out because its current distance is 3. So negative 3 times 1.5 times 1.5, that will give us negative 4.5. And lastly, this point here, negative 4 times 1.5 will get us to -6. So looking at those orange points, I hope you can see the horizontally dilated version of this original function. Which looks something like so. And obviously these points here continue outward. And there we have it. Alright, so hope that gave you an insight into more dilations. Hope to see you in the next video, and best of luck.